Hello to all participants. I will present second training session of cylinder water jacket in AVL FireM. I will show the pre-processing of mentioned model. Introduce myself. My name is Denis Straub and I am an analysis and support engineer from Maribor, Slovenia office. I am responsible for testing software, validation, verification and also customer support. I will start at beginning of Poly benefits. The preprocessor of FireM has many possibilities, from multi-domain meshing, user-defined boundary layers, to embedding different volume meshes to Poly while avoiding arbitrary interfaces. Related graphical user interface is fast, reliable and modern look. In today's session, I will introduce you how we can get mesh from importing the surface with preparation to make quality check and surface repair. Next input what is required is creation of selections and edges. And finally present the advanced mode of frame meshing process. On importing surface with 14 domains, it is suggested to check all of the domains. I demonstrate to you the all corresponding domains. First is cylinder head, the second one is water cooling jacket, and the rest of the domains belong to intake and exhaust valves, seats and guys. The quality check is required as next important step. To handle with the problems in surface mesh, some practice is needed. Which or what should be fixed? The major goal is to produce a clean, watertight surface for meshing. The often artifacts are usually came from imperfect cut triangulation and faulty constructed cut geometry. The next second step which should be applied is selection definition. In this example, we already predefined required domain selection and almost all boundary selection. It is not intended to show creating all of the selection. I will show only additional boundary selection for inlet and outlet. All selections will be transferred to polymesh. The last step before meshing is creation of sharp edges. In first roll, the edges can be made by automatic detection, and also possibility to manually generate edges depend on the chosen selection or chosen domain. The figure on the top left side shows us the edges for our demonstrating cylinder head model. I will show how to add edges by manually with trajectories and also the shortest path over the valve seats. And finally, the frame meshing procedure. The cylinder water jacket multi-material is complex geometry and some local refinements are required for meshing. I would like to explain the advanced mode of meshing. The basic options include surface and volume target cell size, number of boundary layers and boundary layer thickness. The Analyze button will check corresponding surface and edges and their self-intersections and also watertight of the surface. After setting all necessary parameters from basic options over discretization settings to boundary conditions, the user should apply it just to create a polymesh. Multi-domain polyhedral mesh is created within certain time of 5 minutes with previous show settings. The mesh is coarse with approximately 200,000 cells. It can be also finer. On the end of the pre-processing session, I will perform the final check and found that the mesh is suitably prepared for CFD simulation. Now we switch to live. After opening new FireM, we will import the surface to 3D viewer. While surface is loaded, we will perform the surface check in Surface Repair tool as first step. The surface should be activated in element 3, also possible to activate it in 3D viewer. Start Surface Repair tool. The new workflow window is pop up automatically. Now run all the checks. While observing the artifacts, we found that no duplicate elements, small facets, manifolds, cracks, or self-intersections are not present in surface geometry. Some folded patches consist in surface. As auto detection, select in fix area as do nothing. We could leave those patches in geometry. For demonstrating a few folded patches, we will repair to see the workflow for repairing. After selected them in the table, they are shown in viewer on surface. For creating cut view, we can double click it on selected and also with the right mouse button perform the cut view. For such very jointly patches, is the best to delete them and add new patches. We go the whole, but we will delete some additional triangles by manual picking in Selection Creation ribbon bar window. We can also apply different visibility as triangulation on surface. After selecting triangles, we remove them by pressing Remove in Geometry Tools. We repeat the step for others. Now continue to repair holes and find open edges. The hole is found and edge is generated. After pressing Close Hole, the patch is generated just on one side, clearly and precisely closing the hole. Repeat the procedure for second patch. Now let's perform the final check. After all check marks are green, we can continue forward. For undo the view, we use in visibility window Reset Cutting Box. The next step is checking selections. This we can do in element tree while expand toggle switch. We can check domain selections and boundary selection by activating and coloring them in element tree. Using Ctrl and Shift button also help to do this. For creating selections for inlet and outlet, we will use angle-based selection. We change the angle to 15 degrees and now select inlet of water cooling jacket. For saving selections, the Save button is used in ribbon bar. Add a name, BND underscore inlet. Then repeat the procedure for BND outlet. If the name of selection has prefix as BND, INI, or else, the selection is automatically saved under a specific folder with a given name. Now we continue to create sharp edges on surface geometry. The cut geometry has to be activated. By pressing Edge Detection in ribbon bar, we have to define parameters for locating edges. From default values, change 20 degrees for angle threshold, 10 mm for minimum edge length, and 10 mm for minimum number of segments. Now I will apply Detect Edges. While edges are generated automatically, we should merge them to geometry and store to element tree in the project. While the same unnecessary edges were created, we can manually delete them from saved edges. I will remove them with angle-based selection and also polygon-based removing. I will show how to remove edges with polygon selection. Go around the edges and confirm with Enter button, then press Remove. Now we will continue with removing unnecessary edges around guides. I will use an angle-based selection and repeat the step, confirming with Enter and select Remove from the ribbon bar. Now we click on an edge near guide. While some edges are selected, they are highlighted and can be removed. For prescribing all necessary edges, we can add them manually over selected domains or boundary selections. In element 3, I will select selection of intake and exhaust seats, and after they are visible in viewer, click on duplicate the selection. The new geometry is created and shown as mesh copy in 3D viewer and also in element 3. Multiple selected selection can also be applied to generating edges on it. Select only seats as mesh copy in element 3 and open one more time edge detection window. Switch tab angle to trajectory and select define trajectory. The first click on a model is location of origin and second click present direction of edge around. Let's repeat this step for all sharp edges on valve seats. For completing operation, we should save all trajectories to edges with merge and store. For joining auto-detect edges and manually done edges, we select them both in element 3 and combine them with action in geometry tools. Previous created edges can be removed from the project. Now we can also delete the mesh copy from intake and exhaust seats. Now we have created edges and the surface only inside of the project. I will save the project now. So the name is given as Fire M1 and the prefix is PROG. Let us to proceed to final step in pre-processing session. In tab menu, go further to automatic meshing. We can start now new frame poly meshing. Then switch to advanced mode of meshing. If in the project only one surface and one edges exist, they are automatically selected in chosen menu. Press Analyze button. It will check fitting of corresponding edges, self-intersection, geometry check to water tightness and also number of domains. If all checks are passed, we can continue to set the meshing procedure. We got 14 domains. We will set basic options for meshing. As for surface target cell size, we use 2 mm, for volume target cell size 4 mm, and one boundary layer with 0.5 mm of thickness. In meshing setup, we can check domains and change type of state as solid and fluid. After meshing, the domain name will be as selected state. So FL for fluid and SO for solid. In partition section, we can define constraint for automatically generated partitions. If we want to generate the mesh from exactly the same vertices as surface have. This is used in embedding option. As we continue to discretization settings, the local refinements are also based on domain, selections and partitions. The toggle switch for auto refinement is activated by default, and minimum cell size also defined over basic options of target cell size, divided by 10. As in this example, we have multiple small domains. We will generate mesh with the refinement based, considering intake and exhaust valve, seats and guides. I will just deselect cylinder head and water cooling jacket domain. They are bigger. Also, one important setting in discretization is growth rate. It is prescribed by default value as 1.5 in surface and volume measure settings. This means that cell size from surface grow from 2 mm to volume cell size to 4 mm inside the volume mesh. This consider reducing number of cells in whole domain. We can also avoid growing cells inside by specifying a refinement depth. For refinements, we have also other possibilities, as use datum object as cylinder, or cone-based refinements for spray model. Afterwards, we change the surface and volume target cell size to coarser, with reason of less cell count. Change surface target cell size to 5 and volume target cell size to 10 mm. Under boundary settings tab, we can set all global parameters for boundary layer and also defining thickness of boundary layer on desired selection. Connecting edge can be applied to partitions of model, which were created automatically. One possibility is also to pick them from geometry in 3D viewer. The last step is experimental settings. They are used for complicated geometries, for embedding, decoupling multi-material mesh, and few other settings. In this session, it's not intended to explain all of the features. The related check mark in experimental settings is for decoupling multi-material mesh. It is activated by default and will produce all domain interfaces in multi-material mesh with name as DIF_1 and _2 and the rest of the interfaces. After setting all parameters for meshing, we can execute meshing procedure by pressing Create Poly. The meshing procedure is done. The poly mesh is uploaded in 3D viewer and placed in element tree under volume. Expand node of volume and perform the checks of created poly mesh. We use check set for frame poly. Press on check button. Algorithm will check if in mesh persist any identical vertices, negative volumes, invalid convectivity, skewness, cell orthogonality. We can apply observation to specific domains. I will activate water cooling jacket and intake and exhaust seats, valves and guides. We can play a little bit with visibility options in ribbon bar, from creating cutting views with wireframe or transparency view. It's very simple to adjust a view with toggle cursor. We can move cut to the right position. With this slide I will end my presentation of IRM which is highly automated frame meshing tool designed for multi-domain simulation and with different meshing approaches for different type of problems. I would like to thank you for your attention.